Hello and welcome to EngPhys 3BA3 Lecture 11, JFETs and MOSFETs. We don't have too much time to get into FETs in 3BA3, so this is going to be more of a qualitative discussion of how they work with a little bit of calculations, but we're really just spending one lecture on this. So, FETs. Bipolar transistors are commonly used for controlling large currents, but aren't small enough or fast enough for computer chips. For chips, you need to use FETs. In a BJT, we had a barrier to modulate the current. In a FET, a conducting channel is used, and the standard terms are gate, source, and drain. So the gate is the control, the source is like what the emitter was before, it's the source of charge carriers, and the drain is the drain of charge carriers. The gate controls, is like the gatekeeper for how many charge carriers can get through this channel. This is called an N-channel FET. This particular kind we're looking at is a J FET or junction FET. Circuit symbol looks like this for the N channel. You apply a positive, if you were to apply a positive gate voltage, then what will happen is you'll have more negative charge carriers piling up here, like going and flowing here and increasing the negatives in this region, which makes it easier for electrons to flow from source to drain. Now that would forward bias this junction, so that's actually not what you do. What you do is, if you apply a 0 volt at the gate relative to the source, then current can flow from drain to source. But if you were to apply a negative voltage here and reverse bias this diode, then you would be forcing these electrons, these charge carriers here, out of this region, increasing the depletion region of these diodes, which stops current from being able to flow between drain and source. So current would flow from drain to source. You'd normally have the drain at a higher voltage than the source. Electrons would flow from source to drain. Okay, so here's the IV curves for a JFET, for this JFET that we're showing here, this N-channel JFET. And it looks very similar to BJT characteristic curves. A couple of changes. We've got the drain current versus drain source voltage, so that's just the name changes there, rather than collector current versus collector emitter voltage. Big change, though, is that these curves are now not based on base current, but based on the gate source voltage. So this is a voltage controlled device rather than a current controlled device like the BJT was. So with no voltage applied at the gate relative to the source, we've got the most current, we've got the least resistance here, and as we apply lower and lower voltage at that gate, we cause electrons to get out of this drain source region and make it more difficult to conduct between them. This over here was what we called the active mode for a BJT, and on the left we called that the saturation mode. Just to be, because of how FETs are used, for a FET, this over here is called the saturation region, and this is called the linear region. So you'd, the sort of standard operating range or operating region of a FET is over here in the linear region, and if you apply too much drain voltage, then you start to saturate the channel. So what happens is if the drain voltage gets too high, then it reverse biases the PN junction up at the top, and with increasing drain voltage, then yes, you get more voltage between drain and source, but you also have more resistance between drain and source because you're causing those electrons to flow out of there. So that it kind of counteracts itself, and you have kind of a steady current versus voltage relationship. So check your understanding. Why doesn't current flow from drain to gate? So why doesn't it just flow from drain to gate? Well, the answer is because this is reverse biased. If you were to forward bias the junction, then it would flow from drain to gate. The JFET has a natural capacitance similar to a diode because of this charge separation. So you've got a reverse bias diode there, and so this has a capacitance, which means that it's going to behave oddly if you go to frequencies that are too high. It's going to start to conduct where it normally shouldn't. So in the normal mode of the JFET, where you have the gate at a negative voltage relative to the source and a more negative voltage relative to the drain, then no currents flowing into the gate, unlike in a BJT where you needed some current to flow to make it work. Okay, so critical differences summarized. IDS is the IDS versus VDS curve is set by gate voltage, not the base current like it was for a BJT. In a FET, the regions are linear and saturation. In a BJT, they were saturation and active. FETs will conduct with 0 applied gate voltage relative to the source, but BJTs require base current to operate. JFETs can be used to limit current flow in a circuit to a maximum value or to create a constant current source because of the way the curves work here. This is a current source, so it's going to have mostly a fixed current going through here. Think about how this works. If we increase the resistance, normally what would happen is the current would decrease. But because we've now reduced the voltage at the drain, this reduces the FET resistance. So if this resistance goes up, then this resistance goes down to compensate, and we have about the same effective resistance until the point where we push the FET into the linear region. So this would work in the saturation region. Let's use an example of, let's sort of explore that a little bit with an example. Using the IV curves here, determine the current delivered by the current source of figure 523, this one, with Vs equals 10 volts. So find the load line of this, that is, and determine the maximum resistance before the current will droop. So the load line is just the relationship that the current through this resistor is equal to the voltage across it divided by its resistance. And there that is. The voltage is the Vs, which we said was 10, divided by RD, minus RD rather, divided by RL to get the current. And where is this going to stop working as a current source? It's going to work well as long as we're in this region. We know we're on the top curve, VGS equals 0, because the gate is actually tied to the source. So voltage of the gate relative to the source is 0. It's going to stop working as a constant current source as soon as the load line would not pass through a horizontal part of this, but would now be shifting from up there to over in the linear region. So since the since the bottom intercept of the load line is at 10 volts, we can sort of draw some lines and see, well, if we go from 10 to 15 diagonal here, that's when we're just on the cusp of going into that linear region where it's not going to be a constant current source anymore. So that's at 15 milliamps, and solving this equals 15 milliamps for RL. We 15 when VD is 0, that is, for RL. We come up with RL is about 670 ohms. Exercise 530, design a current limiter using a JFET. The circuit should prevent increase of current through the JFET when the current through a resistor in the current path reaches a certain value. Okay, first step is to notice that this is not the same question that we just did. Last time was, how can we use a JFET to make a constant current source? So this is going to have a fixed current going through it, no matter what the resistance value is here. This one, we want to stop, just allow whatever current until the current tries to reach a certain value, and then we want the resistance of this element to shoot way up and stop any current. Well, here's a way to do that. So look at how this works. If the current is low, then we've got the voltage of the gate relative to the source, which is at the other end of this, is pretty much 0. So this behaves like a FET, which has a very low resistance normally. But as current increases, then we start to increase the source voltage, which means the gate relative to the source voltage gets more and more negative. So we're dropping down from one curve to the next, to the next, to the next, to the next. Eventually, we reach the point where we've pinched off the transistor. The gate has enough of a negative voltage on it relative to the source that we've pushed all of those conduction electrons out of the channel, and we don't allow any more current to go through. Okay, next up is MOSFETs. A MOSFET is a metal oxide semiconductor FET. So it's similar to a JFET, except for a couple of changes. So the circuit symbol's different, take note of that. The other thing that's different is that now, because of this oxide, we don't have to worry about what gate voltage we apply. There's no way that we're going to have DC current flowing from gate to drain or source. For the JFET, it was a diode, and so we had to be careful not to hook it up wrong. If we were to apply a positive voltage to the gate relative to drain or source, then we'd just flow a lot of current through it. Not true for the MOSFET. The MOSFET has this insulating oxide there, so no current getting through that gate. In AC, current can still flow into gate because that's just a capacitor. The oxide is typically very, very thin. In computer chips, the dimension that you hear for the technology, so you may hear something like 15 nanometer technology, that's referring to how thick the oxide is. The oxide has been getting thinner and thinner and thinner over the last, like 50 years, as transistors get more and more miniaturized to allow us to make faster and more powerful computer chips. Anyway, the oxide is quite thin, so in new devices, sub 20 nanometers. Now, if you're watching this in the future, then feel free to laugh at how quaint the thinness of our oxides today are once you've got your 1 nanometer quantum computer oxides. Anyway, so the oxide in a FET, quite thin, still no current flows through there in DC. And the other change in the MOSFET is that we've got N plus and then a P region and an N plus region at source. So that means that we can't flow anything from drain to source. So how does this work? Well, we have to apply a positive gate voltage to cause these holes to flow out of there, and the minority carriers, the N carriers that are in here, to accumulate next to the oxide, creating an inversion of the semiconductor that makes an N channel. So this is an N channel MOSFET. The difference between the JFET is that with no voltage at the gate relative to the source for the JFET, you can have, that's when there's low resistance from drain to source. But for the MOSFET that we've got here, you have to apply a voltage at gate to get a channel that allows you to flow from drain to source. So electrons flow from source to drain, but in the N channel, the current flows from drain to source in normal operation. This is what's called an enhancement mode MOSFET. There's another kind called the depletion mode MOSFET, which works just like a JFET in that you have to, with no gate voltage applied, it still conducts from drain to source. So there is a channel with a gate voltage of 0 relative to source. But it's still true for the MOSFET that you can't flow current into the gate. It's still got that oxide. So that means that for the enhancement mode or the depletion mode MOSFET, you can take the gate voltage positive or negative to increase or decrease the resistance from drain to source. The difference between enhancement and depletion mode MOSFETs, for our purposes, is what the resistance is when the gate voltage is 0. For enhancement mode MOSFET, the resistance is normally extremely high, and you need to apply gate voltage to reduce that resistance. For a depletion mode MOSFET, the resistance is normally very low, and you need to apply gate voltage to increase that resistance. Okay, so here's the characteristic curves for a MOSFET. It's exactly the same as it was for our other FET, except that, so it's still N-channel, meaning that the lower the gate voltage, the lower a curve we go to, except that we're zoomed in, so don't let that throw you off. And as we apply more and more gate voltage, then the channel gets, the curve goes higher. So for this particular set of curves that we're looking at here, you need to apply at least 2.5 volts to get this to turn on at all. So if you don't apply 2.5 voltage at the gate relative to the source, then the channel is pinched off. Nothing can flow from drain to source. But then as you apply more and more gate voltages, we go to a higher and higher curve here. All right, let's summarize these general properties of FETs we've been talking about. No current flows into or out of the gate, at least in normal operation. The drain source resistance depends on the gate voltage. For an N channel, the more positive the gate voltage, the lower the drain source resistance, and the more negative, the higher the drain source resistance. For a P channel, that's the opposite. More negative gate voltage means lowering the drain source resistance, and more positive gate voltage means higher drain source resistance. The default resistance, that is the resistance when VGS is 0, depends on the type of FET. For a JFET and depletion mode MOSFET, it's normally very low, and you need to apply a gate source voltage to increase the resistance. For enhancement mode MOSFETs, it's normally very high, and applying a gate source voltage will decrease that resistance. Gate voltage limits. For JFETs, you have to be careful not to forward bias the gate source or gate drain junction because it's just a PN junction. But for MOSFETs, the gate's insulated, so go nuts. Be aware that in AC, the gate can still flow current in because that's like a capacitor. In their conducting states, all FETs have two regions, a linear region where IDS is ohmic in VDS, and a saturation region where it's not ohmic, it's constant in VDS, and this occurs when VDS exceeds some critical value that depends on VGS. All right, if we had more time to talk about FETs in analog, then we'd probably spend a lot of time doing calculations with this next parameter, transconductance. FETs have almost infinite input impedance and zero output impedance. FETs are typically characterized by a mixed impedance Zm, which is the rate of change of the input voltage with respect to output current. The inverse of this is called the transconductance, Gm, the rate of change of the output current with respect to input voltage, which has units of mhos, inverse ohms, or Siemens. Now, FETs have low transconductance, which means they're usually not very good amplifiers compared to BJTs due to the lower amplified current output given a voltage input. They also have a thin current channel and hence can't carry as much current. All right, determine the output of this circuit for different input voltages and explain your reasoning. Why do you think this would be called an inverter? So let's look carefully at this. We've got an N-channel MOSFET at the bottom and a P-channel MOSFET at the top. So both MOSFETs are enhancement mode. You can tell because of the gaps there. Let's suppose that the input voltage is 0. So if the input voltage is 0, that means that this MOSFET has 0 volts at the gate relative to the source. So it's off. It's got a very large resistance there. On the other hand, this MOSFET has what's its voltage at the gate relative to the source? Well, because this has a very high resistance, then this voltage is going to be raised somewhat compared to this one. Like imagine if this resistance was very high as well, then this would be in between. And so the gate of this one relative to its source is going to be negative. So that's when this P-channel MOSFET is turned on. So that means that this has a very low resistance, and so Vout is just Vs. It gets pulled up to this top Vs. So if Vi is 0, Vout is Vs. If you trace it the other way, so suppose Vi is Vs, now what happens is this can't be higher than Vs, so we've got a higher gate voltage than the source voltage, which means this one gets turned off, so that's a large resistance. On the other hand, this one has to have a higher gate voltage than Vs, which means it's turned on, so it's conducting through the drain to source, so that pulls Vout down to 0. So in conclusion then, when Vi is low, the output is Vs. When Vi is high, the output is 0. That's why this is called an inverter. Okay, design a voltage divider, a voltage-controlled voltage divider that uses one of the resistors as a MOSFET in linear variable resistor mode. Not too much to this, just put a MOSFET as one of the resistors in a voltage divider. Okay, here's a preview of CMOS. This is what we're going to get into in the next set of topics. So once we start talking about, once we get into chapter 7, this is the foundation of digital logic, complementary metal oxide semiconductor, complementary MOSFETs. Here's a complementary MOSFET NAND gate. A NAND gate is supposed to output not the AND of the inputs. So the AND of the inputs would output a high only when both inputs are high. So a NAND should output a high unless both the inputs are high. Okay, all of these MOSFETs are enhancement mode, and the circles are P-channel, the not circle ones are N-channel. This is a typical different way to draw MOSFETs that you would use in digital logic. So once you're talking about CMOS, you wouldn't bother with the more complicated symbols with the arrows and all that. You view MOSFETs as operating in their ideal mode where they're either allowing current through or they're not allowing current through. So the N channel ones down here, if we've got a positive signal, we've got a positive voltage here relative to the bottom, then they allow current through. And the P channel ones, if we've got a positive voltage, they stop current. They allow current unless you've got a positive voltage applied there relative to the bottoms. Okay, so let's trace how they would behave in response to these pairs of inputs, both low, both high, one high, one low, and one low, one high. Assume that they switch their conduction at VGS is above 2.5. Okay, so if, the negative ones, the P channel ones allow it if VGS is less than, really that should be negative 2.5. Okay, let's trace one of these. So if both the inputs are 0, so if A is 0 and B is 0, that means that these ones are both turned off. And so with these having high resistance, just like we looked at in the inverter, that's going to pull this voltage up so that it's higher than 2.5 volts. And so VGS for these P channel ones is going to be less than negative 2.5. And so we've got like at least 2.5 volt here. That means that these ones start conducting, and so this gets pulled up to 5. So if all the inputs are 0, then this is 5 volts. If all the inputs are 5 volts, on the other hand, this is just like the inverter in the opposite in that case as well. So we've got high voltage here that lets these conduct, that pulls this down to 0, which means these ones are now turned off, and so they stop conduction, and so the output is just 0. Now let's look at what happens when one of the inputs is high and one of the inputs is low. So if this input is high and this one's low, this is, and down here as well. So if this is high, this is low. Because this one's low, it's got really high resistance. The fact that this has low resistance doesn't matter. It pulls, it stops any conduction from going through there. And on the top side of it, we've got one of them conducting, one of them not conducting, which is going to, the not conducting one doesn't matter on this side of it because they're in parallel. So the output gets pulled to high. Same thing for this opposite case. So the output is going to be high if both of them are off, or if one of them is conducting. The only times the output's going to be low is if both of them are on, which means this is indeed a NAND gate. Try and use this to design a CMOS NOR gate, one that would be low unless both inputs are low. Well, all you do is reverse which side of this was in series or parallel. The beautiful part about CMOS is that for either of these situations, there's no current flow from top to bottom. So any path the current would try to take to go from top to bottom under any of these input circumstances is going to be blocked by a closed off, a pinched off MOSFET. And the MOSFETs have incredibly high resistance in that region. So this one thing, being able to build CMOS using MOSFETs, and the fact that we can build MOSFETs really small, is what allows us to make computer chips that don't just blow up from the amount of heat that they're putting out. We can have billions of transistors in a computer chip and be operating all of them at decent voltage because there's very, very little current going through them. All right, one final point here. BJT transistor logic, TTL, and a cautionary note. So CMOS is technically a form of transistor logic. When most people say TTL, they mean BJT, transistor logic. They'll call CMOS, that is MOSFET transistor logic, just CMOS. So you can make BJT transistor logic, something similar to the circuits we're looking at with MOSFETs, with a circuit like this. So this is an example of using BJTs to make transistor logic. And this is used still, even though MOSFETs are very common for computer chips. For bigger chips where the size and the heat advantages of MOSFETs don't really come into play, and you'd rather just have larger currents possible, then BJTs are often superior. So you have to be aware that these circuits exist as well. And because BJTs are fundamentally current devices rather than voltage-controlled devices, they're often incompatible with CMOS. So it's really important for you to know which kind of a chip you're using, because we have both in the lab. So if you just go over to the side and you grab like an AND gate, you have to look up what part it is and see whether it's TTL or CMOS, and not and be careful how you're hooking up one to another one. So you one of the ways that this manifests is that the acceptable voltages for TTL are often different than they are for CMOS. So if you've got a TTL gate and you've got a CMOS gate, then where they decide that the voltage is high or low, and what they'll output as their opinion of that may not match. So you could have odd behaviors in using a CMOS inverter here and a transistor logic NAND gate.